let's move on to the next big part of chapter 7.4, which is about surface area for solids of revolution. So imagine if I took this shape and rotated it around the x-axis, but now I'm not asking about the volume, I'm asking about the surface area. I would get kind of a pear shape with a pointy bottom. So what's the surface area of that? Well, what did we do last time for volume of revolution? We segmented it into cylinders, right, into thin disks. So we could imagine drawing kind of a disk or a cylinder like that, and another one like that, and another one like that, and another one like that, and then spinning each of those around. So can we approximate surface area as the surface area of these cylinders? Well, anything's an approximation for anything, right? Big question in calculus is, would the approximation get better if you used more cylinders that were each narrower? Hopefully it would. To think about that, let's step back from this whole 2D, 3D rotation thing and just think about triangles. And arc length. Let's think about a classic right triangle that's called the 3, 4, 5 right triangle. So we'll say 3 there, 4 there, and 5, right? And we know that's 5 because 5 is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, which is the square root of 25. Remember, you can't just use the square root to cancel the square and the square, because then you get 3 plus 4, which is 7, and is not 5. All right, so what if I wanted to approximate that arc length by going over and up, over and up? So if I have this, that total length of 5, but I try to approximate it by going over and up and over and up and over and up and over and up, how far over did I go? Well, I went 4 centimeters or whatever over. What's my total distance going up? Well, I did it in little jumps, but overall I went 3 centimeters up. So I get 7 centimeters. What if I did it using smaller steps? So I'll do the same thing, but I'll go over, up, 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 over, up. That looks like a better approximation. How far over did I go total? Still 4 centimeters, right? And how about total up? Still 3 centimeters. So I did a lot more work, I did a lot more steps, each of them smaller, but my answer did not improve at all. So the same thing is going to go on here in this case, where the area that, or the surface area that we're missing is kind of this slanted thing, and we'd be approximating it with cylinders that go over and maybe a little bit up, and it's just not going to work out. So we'll say approximating the surface area with cylinders won't get better as you use more cylinders. So what do we do instead? Well, here we had to use something like Pythagorean theorem and think about slanted edges going along a diagonal, not over and up. So what we do instead, in the surface area case, use a slanted cylinder, but if a cylinder starts like this and you slant both of them like that, what are you getting? A section of a cone. So you're getting a circle there and maybe a bigger circle here. And then taking the surface area of that. That itself, I'll let the book explain it for you. So I'll say see the book's explanation and diagram. So the key part is we're asking what's the surface area of this slanted thing. So overall, the formula the book gives us for surface area, it's familiar with the arc length thing, but it has an extra wrinkle thrown in. Integral from a to b, 2 pi f of x times square root of 1 plus f prime of x squared dx. And this, does that look kind of like the volume by shells formula? 2 pi times something. There, the f of x was the height, and that we had an x here that was the radius, and then we were doing the circumference by spinning that all the way around. Here, this f of x is a radius. Notice, remember, we're circling around the x-axis here, so f of x is a distance from the x-axis, and so that's the radius of this thing that we're spinning around. So that's kind of where that formula comes from and why we can't just use cylinders which have kind of nicer formulas.